from India. And good day, good morning, good afternoon, wherever you may be. Thank you for this platform to speak. And I'd like to show you our fairly disruptive hydrogen-free, low-carbon catalytic desulfurization process. This is, I would say, one of the lowest carbon processes today in the world for reducing sulfur from the petroleum stream. The growing desulfurization market in the world is today out of the 1 million barrels per day of global refining capacity. There is probably somewhere between 1 to 4% sulfur in the feed stream. So we're talking about trying to remove at least 1 million, maybe up to 4 million barrels a day of sulfur in the global system. And by 2030, because everywhere, especially from our first keynote speaker, we know that an increase in sulfur levels will cause increase in refining capacity, because the sulfur has to be taken out of the fuel so that it does not become sulfur oxides on combustion. Today, the leading technology for sulfur removal is hydroprocessing. Typically, that's called hydrodesulfurization. It is one of the fastest growing technology sectors in the world, and we'd like to offer you an alternative option to hydrodesulfurization. Without going to a very complex refinery diagram, because I can see that a lot of the colleagues on the webinar today are from academia, we can just see that all the portions that are marked in blue produce sulfur-rich streams, particularly H2S gas. And that H2S eventually has to be then converted to elemental sulfur, because hydrogen sulfide cannot be emitted from a refinery. It is toxic, and of course, it also smells awful, but it is extremely toxic. So it is converted to elemental sulfur, and then these mountains of elemental sulfur have to be moved over large distances to their applications. And anytime we move any material over hundreds of kilometers, we add a carbon footprint, because typically all movement takes place using fossil transportation fuels. Typically, petroleum products contain, as I said, significant quantities of sulfur. The heavier the cut, the more the sulfur. And globally today, there is a lot of pressure on heavy fuel oil and bunker oil for ships. And this is being pushed down for shipping applications to 0.5%, which means that there's further desulfurization needed globally to accommodate those demands. Conventional, like I said, hydrodesulfurization is common, but there are a number of other possible hydrodesulfurization designs today. And then that hydrogen sulfide that is produced must be further processed, involving a further carbon footprint, to sulfur dioxide, and then through the Claus process to elemental sulfur. Non-hydrodesulfurization options, even though plenty of them exist, have not really gained large traction, because hydrodesulfurization is easy and you can build very large units, but the environmental impact of hydrodesulfurization is very significant. Also, the heavier the crude oil or the petroleum cut, the harder are these molecules to remove and to desulfurize. These are all aromatic compounds. We can call them sulfur-containing heterocyclic aromatic compounds, or SCHACs or SHACs. And these are, the more of these you have, the higher the temperature and pressure that is needed for the desulfurization process. And the higher the temperature and pressure, the more the carbon footprint of the process. Also, it's a destructive method. So eventually that sulfur is gone, and it's gone as elemental sulfur. You have to reform that sulfur into something useful. And again, industrial process will be needed to make that sulfur functionally usable. Sulfur is also a very light material, so it takes a lot of space in storage and a lot of energy in handling. Our desulfurization process is absolutely novel. Patents have been filed for this. It simply removes the sulfur as a value-added sulfur product, which we will call an SBA, a sulfur-based additive. And it is simply nothing but you take the high sulfur refinery stream or even crude oil. We add to that a particular catalyst. We just stir it in optimal conditions, atmospheric pressure, and a temperature which is adequate to make the system flow. The SBA precipitates out and is simply separated, and the desulfurized crude oil can then be processed further in the petroleum process. in almost every parameter where we compare it with conventional hydrodesulfurization, our desulfurization process is dramatically better. It's not mildly better, it is significantly better. And it solves most of the major problems that lead to a refinery's greenhouse gas footprint today. We believe that this has the opportunity to be disruptive in millions of tons a year. How disruptive? Here are some examples. In fact, with the lighter streams, naphtha and gasoline, the sulfur reduction is not too much. It's significant, but it's not dramatic. But the moment I go to a heavier stream like light cycle oil, which is typically blended into fuel oil, we're getting a 90% reduction. So you would reduce the hydrodesulfurization load by 90%. Similarly, for vacuum gas oil, which is the residue from the vacuum column of refinery, you get 77% reduction. And this is especially exciting because those are the more difficult items that to desulfurize. Even directly with crude oil, with the different crude oil samples that we were able to obtain from refineries in India, we are able to get between 14 and 43% reduction. And that is not insignificant because it will reduce the amount of corrosion in pipelines and also the amount of sulfur that has to be unnecessarily transported through millions of kilometers before it is then desulfurized in a refinery. What do we do with this sulfur-based additive that is produced? We are seeing some very nice results in bitumen upgradation. Bitumen anyway is a petroleum stream. So adding a petroleum-derived sulfur system like our SBAs is producing fairly interesting results and driving up base bitumen properties to higher bitumens. Particularly the higher the bitumen grade that we go to, the higher VG we go to, the more efficient it is for laying road pavements and the higher the performance of the road that you lay. VG40, VG30, increasingly higher grade numbers command higher prices in the US. Therefore, using a low-cost sulfur-based additive derived from crude to make bitumen will give very significant financial benefits. And we can see here that by adding this feed in different bitumens VG10, we are able to start attaining the properties which are similar to VG20 or 30 or 40. And that tells us that not only are we able to desulfurize crude, we are able to create higher value from the desulfurized crude at a much lower cost than any known refining process on earth. Patents have been filed globally and in India. Trademarks have been filed in India and in Kuwait and also in many other countries. They're not yet granted. And we believe that our novel hydrogen-free catalytic desulfurization process is the most exciting thing the world has seen in sulfur reduction. We believe that the product that is produced from the system, which we call an SBA, can upgrade bitumen, and therefore there's a high volume application available. To meet marine fuel standards, which require very low sulfur fuels today, this is the only disruptive solution of its kind. It is not yet scaled up to industrial scales. And therefore, industrial collaborative research opportunities are open for people who would like to partner with us and take this to global scales in thousands of tons. The benefit of this kind of work, where we have a low cost, low investment, but high impact disruption, is that we will have a safer, nicer, kinder, and lower carbon environment. I'd like to acknowledge my parent organization for research funding, the organizers for the opportunity to present our work, my co-authors, and the refineries who provided us with samples. Thank you very much for your attention.